Very good evening to all the attendees who have joined today in this special public lecture, which is being jointly organized by the National Academy of Sciences India Delhi chapter and the Science Foundation and Ministry of Education supported Institution Innovation Council, the Dayal Upadhyaya College, University of Delhi. And this lecture is being organized under the aegis of the DBT Star College program. And today we have with us on the panel, Professor Anthony J Leggett, who's a Nobel Laureate Physics, and Professor Emeritus, Department of Physics, Grainger College of Engineering, University of Illinois. Professor Anurag Sharma, who's the Chairman of the National Academy of Sciences India Delhi chapter. Professor Vinay Gupta, who's the Chairman of our college governing body, and also a very senior professor at Department of Physics and Astrophysics, University of Delhi. And our principal, Dr. Hemchand Jain. So first, I would like to invite Professor Anurag Sharma to say a few words, and followed by Professor Vinay Gupta and Dr. Hemchand Jain. Over to you, sir.
Okay. So good evening, good morning. It's my pleasure to be here, to be associated with this lecture by Professor Leggett. And it is so fortunate that within a span of less than 2 weeks that I am interacting with Professor Leggett again. I mean, it's really a pleasure that you don't get so often that you are meeting a Nobel laureate twice within a span of 2 weeks. My job here is to introduce NASI, which is the National Academy of Sciences in India. We are associated with the Delhi chapter of this particular academy, NASI. This academy, NASI, is the first academy to have been started in India in 1930 or so, and it was started by Professor Meghnad Saha, who was a well-known thermodynamics, statistical physics, astrophysics person. His equation of ionization is the most famous equation of which has led to many inventions and discoveries in astrophysics also. And so this was started way back about 90 years back now. We are going to celebrate probably 90th year this year. And Delhi chapter of this was, so there are many chapters of this academy all over India. Delhi chapter was started in 2008. And for many years, Professor Rekhi Ghatak, who has been my mentor also, has run this chapter very efficiently and ably. I have just taken over from him, and I hope to do as well with the support of persons like Manoj Saxena and many others. And so this chapter also organizes seminars, supports some undergraduate research, some programs, training programs, and things like that, like any academy would do. So this is what we also do. And in the same vein, we are actually supporting this lecture also. So it's really a pleasure to have Professor Leggett for this lecture, and we look forward to listening to you.
Thank you. Thank you very much, sir. I now request Professor Vinay Gupta to kindly introduce the gathering.
Good evening, everyone. I welcome Nobel Laureate Professor Anthony J Leggett and Professor Anurag Sharma, Chairman NASI, for in the first webinar of the series of the lectures, which has been jointly organized by the National Academy of Science and DDU College. DDU College has secured 15th rank in National Indian ranking framework, and the Science Foundation of the college has been very active in organizing seminars and conferences. We have seen that. Quantum mechanics is one of the most fascinating subjects to such study and has revolutionized the development of sciences. So to summarize, basically what I want to say that the richness of quantum physics will greatly affect the future generation technology in many aspects. Because of this, quantum mechanics is an essential component of the undergraduate curricula, including electronics, physics, chemistry, and many areas of science and technology. And I'm sure that through this special public lecture, students and faculty members will drive new energy to work in this emerging area of quantum computing, quantum materials. And I requesting all to please join me in welcoming again Nobel Prize honored Professor Sir Anthony J Leggett. Thank you to all.
Thank you very much, sir. I now request our principal, Dr. Hemchand Jain,
Thank you, sir. I'm
to
welcoming.
say a few words. Yeah.
Thank you, Dr. Manoj. On behalf of Deen Dayal Upadhyaya College, I welcome Sir Anthony J Leggett, the Nobel Laureate in the area of physics, Professor Anurag Sharma ji, who is the chairman NASI Delhi chapter, and Professor Vinay Gupta ji, chairman governing body Deen Dayal Upadhyaya College, and also a very senior professor in the University of Delhi in the Department of Physics. I welcome all the participants on the special public lecture by the Nobel Laureate, Sir Anthony ji. Deen Dayal Upadhyaya College is the ranked 15th college in the NIRF ranking framework of the Government of India. The college was established in the year 1990, and in the last 30 years, the college has reached to a situation where we are among the top 15 college of the country. I think now it is the time when we would like to listen to the Sir Anthony ji on the topic for which we all are eagerly waiting for. Thank you very much.
Sure.
Thank you.
So thank you very much, sir. And now I'll be sharing the screen.
Well, thank you for the introductions, and good evening, everyone. If in the year 2021 we look at the current state of physics, then with the possible exception of cosmology, I think we find that it fits very well the definition of what the late philosopher and historian of science Thomas Kuhn called normal science. That is, it's a science in which the kinds of questions one is allowed to ask, the sort of answers you're allowed to give to them, and the evidence which you're allowed to adduce in favor of those answers is all pretty much agreed in the relevant community. And therefore, you would expect that discussions among professional physicists about technical issues in physics would not generate the sort of intense feelings and emotional involvement which we're used to seeing, for example, in discussions on, say, politics or even the social sciences. And yet, there is one issue which generates precisely such extreme passions. As I found when I was young and mischievous, I used to occasionally go to cocktail parties at physics conferences, and I would lob this issue like a hand grenade into a group of unsuspecting physicists and stand back and watch the results, which were often quite spectacular, to the point that in one or two cases it almost seemed there would be blood on the floor. So what is this contentious issue? Well, in the mid and late 20s, the community of physicists at that time, having failed to understand the behavior of matter at the level of single electrons and atoms in terms of what they would call mechanics, and we would now call classical mechanics, they then evolved a way, what is not just a new theory, but really a new way of looking at the world, which we call quantum mechanics. In the roughly a century since then, quantum mechanics has really been spectacularly successful. It's been able to describe not only what it was originally intended to describe, namely the physics of single atoms or electrons, but the many much more complicated things from the psychophysics of human vision up to meteorology. And right now we have no evidence that it ever fails. And yet, if you really take quantum mechanics seriously and try to apply it to the macroscopic world, and in this lecture, by the word macroscopic, I mean basically at the everyday level. So if you try to apply quantum mechanics at that level, then you get some very bizarre results indeed. So is that a problem? Well, that depends whom you ask. On the one hand, we have, for example, the late Professor Leon Rosenfeld commenting on a particular paper in this area and saying that these authors have totally resolved all the apparent paradoxes in applying quantum mechanics, leaving no loophole for extravagant speculation. On the other hand, we have the late Professor Edwin James, who, in a famous quote, said that the picture of the world given by quantum mechanics has more in common with medieval necromancy than with science. So, what is this issue then which has raised such intense passions? Can I go to the first slide, please? Good, thank you. So let's consider a very general thought experiment. Many of you will recognize that one possible implementation of this thought experiment is the famous Young-Slitz experiment conducted with single electrons or neutrons, say, but it's much more general than that. We consider a set of microscopic entities, perhaps electrons, neutrons, let's say for definiteness atoms. A set of atoms which can start from some initial state, A, and then reach a final state, E, where their arrival is directly inspected with the naked eye. And to get from A to E, the atoms can go through one of two channels, either B or C. And we arrange that we may decide to inspect which of the channels a particular atom goes through. We do that by opening the shutter at the top of the slide and directly inspecting whether the atom goes through B or not, and similarly with C. Or on the other hand, we might decide not to inspect which path they go through, which we can do by closing the shutter in question. So, this is roughly how the experiment goes. Let's first shut off possibility C. We assume that in any given case, our experimental colleagues know how to do that. For example, in the case of a simple Young-Slitz experiment, you would simply block the slit C with some opaque material. But anyway, more generally, our experimental colleagues can do that. So we shut off possibility C, and thereby we measure the probability that a given atom starting from A goes through B and arrives at E. And let's call that, by definition, P sub B. Again, we can do the opposite. We can shut off path B and thereby measure the probability that an atom goes from A through C to E. Let's call that P sub C. And finally, we can open both paths and measure the probability that an atom goes through from A through, well, let's say either B or C at first sight, and arrives at E. And let's call that probability P sub B or C. Okay, next slide, please. So what's the result of such an experiment if we do it carefully? Well, first of all, let's imagine that we do actually look to see whether a particular atom followed path B or path C. What do we find in that case? Well, first of all, we indeed find that every individual atom does indeed follow either path B or path C. And secondly, the probability of arrival at E with both the paths open is simply the sum of the probabilities of arrival for each path separately. That's essentially the common sense result. After all, remember, if, for example, there are a number of airline passengers who fly from Chicago to Delhi, and they can go, let us say, either via London Heathrow or via Frankfurt, then the total number of passengers arriving in Delhi from Chicago is simply the sum of those who came through London Heathrow and those who came through Frankfurt. That's just common sense, nothing at all surprising about it. But now let's suppose that we deliberately refuse to inspect which path was taken by an individual atom. Then, in fact, we find that the probability of arrival with both the paths open is not simply the sum of the probability of arrival through each path separately. In fact, we can have that the probability when only path B is open is non-zero. Similarly, the probability when only path C is open is non-zero. But the probability when both paths are open is zero. That's the phenomenon which we call total destructive interference. So this is the raw experimental fact. And what it would seem to suggest is that neither path B nor path C is selected by each individual atom. That's in the case where we don't inspect it. Now, what positive statement you make is perhaps a matter of taste. You might want to say that each individual atom selects both paths, B and C, or that it selects neither path, B nor C, or that the question is just not meaningful. But let me emphasize, the one thing you cannot say under these circumstances is that each individual atom does one thing or the other. Okay, so that's the bare experimental fact. Now let's go on to the description given by quantum mechanics. Next slide, please. Okay, so actually quantum mechanics gives a rather straightforward account of how this works. In quantum mechanics, each possible process is represented by a probability amplitude, A, and a probability amplitude is somewhat different from a probability in the sense that it can be either positive or negative. Some of you will know that the actual, the real state of affairs is a bit more complicated than that, but for our purposes, it'll do to say it can be either positive or negative. And the total amplitude to go from A to E is the sum of the amplitudes to go by different possible paths. In this case, A goes to B goes to E, and A goes to C goes to E. That's the total amplitude. The probability to go from A to E is just the square of the total amplitude. Okay, so let's just do a little rather straightforward algebra. Next slide, please. So I just ask your tolerance for the next 2 or 3 slides for some straightforward algebra. First of all, if path C is shut off, then the total amplitude to go from A to E is simply the amplitude to go through B. And the probability under those circumstances, which by definition is P sub B, is just A sub B squared. Similarly, if path B is shut off, then the total amplitude is A sub C, and the probability, which under these circumstances is P sub C, is A sub C squared. But now here comes the crunch. If both paths are open, then the total amplitude is the sum of A sub B and A sub C. And that is what in quantum mechanics is called a quantum superposition of the 2 amplitudes, or 2 possibilities. So under those conditions, the probability, which by definition is now P sub B or C, that's given by the square of the total amplitude, A sub B plus A sub C all squared, and just multiplying that out, that's A sub B squared plus A sub C squared plus 2A sub B A sub C. So that means that now, if you stare at that expression, you see that we've already decided that A sub B squared is just P sub B, A sub C squared is just B sub C, and therefore the total probability to go from A to E when both paths are open is the sum of P sub B plus P sub C, which by itself would be the common sense result, but plus this famous or infamous interference term, twice A sub B times A sub C. And you can see from this expression that in order to get interference, in other words, to get something other than the common sense result, it must be the case that A sub B and A sub C simultaneously exist for each atom. I emphasize for each atom and not simply for the whole collection of atoms. A sub B and A sub C must exist for each atom separately. Next slide, please. Just one more slide and then we're done with the algebra. So I just repeat at the top of this slide that the probability when both paths are open is the common sense result plus twice A sub B, A sub C. Now let's suppose that for some reason A sub C is either plus or minus A sub B at random for each particular atom of the ensemble. Then the average over the ensemble of P sub B or C is just given by the common sense result plus twice the average of A sub B, A sub C. But if A sub B is equal to A sub C is equal to plus or minus A sub C at random, then that average is the average of A sub B squared and minus A sub B squared and just 0. And therefore, under those conditions, the probability with both paths open is just the sum of the probabilities with each path separately open. And that is just the common sense result. And that result is just as if it's the result you would get if each system had indeed chosen either path B or path C. So what this then, so then the final remark at the bottom is not directly related to the rest of the slide, but it's just to emphasize the fact that if you believe the quantum mechanical formalism, then whenever A sub B and A sub C simultaneously exist, then neither path B nor path C is selected. And that's the point I want to stress. As I say, you can, again, make whatever positive description you like, but the one thing you're not allowed to say under those conditions is that each atom selects either path B or path C. Okay, well, very early on in the history of quantum mechanics, people realized this rather peculiar state of affairs. And they were puzzled, but much of the puzzlement for many people was removed by the famous physicist Niels Bohr. Can we just have the next slide, please? We should have a photo of him, I think. Yep, here we are on the right. And Niels Bohr basically told the physics community, well, there's really no particular reason to be surprised here because, after all, you would not really expect entities at the level of atoms and electrons to behave in the same way as macroscopic, common sense, everyday level objects. It's a very, very crude oversimplification of what Bohr said, but you know, I think gives the essence. And many people, for quite some time, were satisfied with that explanation. But any community always contains ordinary people, that is, people who almost by nature don't accept the standard explanation. And in the case of quantum mechanics, one of those people was Erwin Schrödinger, who's on the left, and was again a famous figure in the foundation of quantum mechanics. And in 1935, Erwin Schrödinger produced a counter-argument to Niels Bohr's argument in the form of a famous thought experiment. Next slide, please. Okay, so crudely speaking, with a few variations, this is the thought experiment which Schrödinger proposed. Let's imagine that we have a group, again, of, let's say, atoms, which start off from some initial state A, and from A, they can go either down path B or path C. And if a given atom, let's consider the first atom, say, out of the box. If that atom goes down path B, then nothing spectacular happens, and in particular, a cat, which is enclosed in a sealed box, remains happy and well. On the other hand, if that atom goes down path C, then it eventually enters some kind of counter. It will trigger some electronics. As a result, a hammer will fall inside the closed box onto a vial of cyanide. The cyanide will escape and the cat will die. And I should like to emphasize that this diagram is historically correct. There's an unfortunate misconception in some quarters that Schrodinger's cat is either shot or electrocuted, but no, in the original she's actually poisoned by the cyanide, and there it is to show. Anyway, so what's the point of what Schrödinger called this this bizarre experiment? Well, it's a very general principle in quantum mechanics that if state 1 evolves into, if initial state 1 evolves into final state 1 prime, and initial state 2 evolves into state 2 prime, then the quantum superposition of 1 and 2 will inexorably evolve into the quantum superposition of 1 prime and 2 prime. Now, in this particular case, initial state B evolves into the state, a state of the universe in which the cat is alive. Initial state C evolves into a state of the universe in which he's dead. But now let's suppose that the atoms are actually described by a quantum superposition of B and C, which we can certainly engineer in principle. Then that superposition of B and C must evolve into a superposition of states of the universe, in one of which the cat is alive and in the other of which she's dead. More formally, the quantum amplitude for the cat to be alive is not we concluded that whenever the amplitudes for two different states were both non-zero, then it could not be the case that each atom or electron realized one state or the other. Well, therefore, applying this, this principle at the level of cats, if indeed that is the correct description of the final state of the cat by quantum mechanics, then the particular cat in question cannot be said either to be definitely alive or to be definitely dead. Now, fortunately, the animal protection societies have prevented us from doing this experiment in a statistically meaningful way, but I think very few of us doubt that in this situation, were we to take the lid off the box, we would see this particular cat to be either definitely alive or definitely dead. So that's the state before we take the lid off, the state described at the bottom of the slide, seems to be very uncomfortable, not only for the cat, but for the theoretical physicist who has to contemplate it. And that is the famous or infamous Schrodinger's cat paradox. Next slide, please. Now, that paradox has now been around for 85 years, and there must have been thousands, maybe tens of thousands of papers, not just in the physics literature, but also in the philosophy literature, which claim to have resolved the paradox. And basically one can classify the possible resolutions of the paradox into two classes, depending on whether or not they assume that quantum mechanics is indeed a universal description of the physical world at all levels, not only the level of electrons, but the level of cats and even perhaps the level of ourselves. So let me first contemplate the possibility that we do assume this. We're going to assume that quantum mechanics is the whole truth. I'm now going to take these three possibilities slightly out of order. Let me start with the extreme statistical interpretation or solution. What that resolution of the paradox says is, look, you're really taking all this far, far too seriously. All that the formulas of quantum mechanics ever was and ever was intended to be is simply a recipe. That is, it's a string of symbols which you write on a piece of paper, or perhaps manipulate in your mind if you're clever, to enable you to start from a given experimental situation and predict the probability of various outcomes of the experiment. So in fact, when we arrive at this final bizarre description in which the quantum mechanical amplitude for the cat to be alive is non-zero, and the amplitude for her to be dead is simultaneously non-zero, well, that's all it is. That is simply the symbols that you've written on a piece of paper have those values. And beyond that, there is no correspondence to anything whatever in the real world. The symbols you've written down and are manipulating have no more reality than the recipes which the ancient Chaldeans were said to have used to calculate eclipses. They correspond to nothing whatever in the real world. They just happen to get things right. Well, let's say that resolution of the paradox does have the virtue of being self-consistent. After all, if a given set of formulae is nothing but a recipe, then how could it be internally inconsistent? The only way would be if different recipes or different prescriptions for applying that recipe were to give different predictions. And as far as I know, that is not true in the case of quantum mechanics. So as I say, it's internally consistent, but it seems very, very uncongenial. And I find, in fact, that experimentalists are even prompter in rejecting this interpretation than theorists are, because it really has the following consequence. The question, what was the correct description of the state of this initial state of this cat? I'm sorry, what was the correct description of the state of this cat before I've taken off the lid off the box and looked at her? That question not only has no answer, it really in some sense is not even meaningful within this interpretation. And I think many people, as I say, including most experimental physicists, find this extremely repugnant. Okay, so if we don't like that interpretation, let's go to the opposite extreme and consider the so-called many worlds or Everett-Wheeler or relative state interpretation. And that really takes the extreme opposite point of view. You remember the statistical interpretation said you really shouldn't take the formulas of quantum mechanics seriously at any level. By contrast, the many worlds interpretation says, yes, take the formulas of quantum mechanics deadly seriously, not just at the level of electrons and atoms, but at the level of cats and counters, and so forth. And indeed, when we have this peculiar description of the cat with non-zero amplitude to be alive and non-zero amplitude to be dead, that indeed is the real state of affairs. It is not true that one or other of these possibilities is definitely realized. But then you say, well, wait a moment, I've just taken the lid off this particular box, and this particular cat seems to be alive and well and mewing happily. What happened to the piece of the description, the amplitude, for her to be dead? And at this point, the advocates of the many worlds interpretation look you in the eye and say, well, what you have to realize is that the world in which you see this cat to be alive and all your colleagues see her to be alive and so forth is just one of many coexisting worlds, many parallel universes. There is another parallel universe in which this cat is dead and all your colleagues see her to be dead. And this parallel universe is equally real to the one you think you're experiencing. And then there are a number of formal theorems, many of which were proved in Hugh Everett's original thesis, which tell you that there is no possibility of, as it were, crosstalk between these different possible universes. Well, I wish I could say something intelligent about the many worlds interpretation, but I'm afraid I can't. And the reason is quite simple. I quite simply and literally do not understand it. When the advocates of that interpretation say that these parallel universes, which I don't experience and could never experience, when they say that these are, quote, equally real, unquote, those words sound like English. What do they actually mean? To me, they're simply words with completely detached from any kind of meaning. Now, I'm probably going to offend one or two people in the audience at this point, but let me just comment that I sincerely believe that when historians of science in the year 2200, say, look back on the early 21st century and the ideas which physicists were embracing, they will be amazed that so many otherwise intelligent physicists could embrace this nonsense of the many worlds interpretation. Okay, so if we don't like extreme statistical interpretation, and we don't like many worlds interpretation, what's left? Well, what's left is what I call the orthodox resolution, by which I imply that it is, I think, the resolution which many practicing physicists fall back on when they start to think seriously about this problem. Let's just recall from our earlier slides that in general, if we have an experiment of the type I considered, then the probability when both paths B and C are both open is not just the common sense result, that's the first two terms on the right, but it also involves the interference term, which involves both the probability amplitudes. However, we also noted that if A sub C is equal to plus or minus A sub B at random, then P sub B or C is the common sense term result plus the average of twice AB sub B A sub C, but that average in this case is just 0, and therefore we just return to the common sense result. Now, generally speaking, unless you're talking about very specially prepared experiments, and we'll come back to that later, generally speaking, the effect of the outside world, what is technically called the environment, in quantum mechanics is crudely and generally speaking to randomize the sign of A sub B relative to A sub C. And that randomization process gets more effective as the system gets larger and more complicated and closer to the everyday level. Therefore, we conclude that the interference term vanishes for everyday objects, let's say, at the level of cats. And that is the phenomenon which is known as decoherence. And so far, I'm totally happy with the argument. But then there's a crucial final step. The advocates of this interpretation claim that, well, since the experimental predictions of the formalism are now identical to what you would have got by assuming that each system chooses either possibility B or possibility C, then we may legitimately say that each system does choose either B or C. And that is what I don't like. That seems to me a very severe logical non sequitur. It confuses the possible and impossible interpretations, legitimate and illegitimate interpretations of the quantum formalism with the evidence that such an interpretation is or is not legitimate. At the microscopic level, we saw that it was not legitimate to assert that each individual system chose either B or C. The reason, the evidence that that was illegitimate came from the phenomenon of interference. Now, by the time we get to the macroscopic everyday level, all of us agree that the evidence has gone away. But does that mean that we are suddenly entitled to reinterpret the meaning of the formalism? I don't believe it does. Imagine an analogy. Imagine a murder trial where, let us say, the accused is supposed to have killed his wife, and there is a crucial piece of evidence, let's say a bloody axe with her blood all over it and his fingerprints all over it, etc., etc. And everyone says, obviously, the accused is guilty. Suppose that somehow, mysteriously, in the middle of the trial, that vital piece of evidence suddenly disappears. Does that mean the accused has suddenly become innocent? I don't believe so. And similarly, I don't believe that simply because the evidence against a particular interpretation of the quantum formalism has gone away by the time we get to the macroscopic level, therefore we are free to embrace that interpretation. So my own view would be that none of these three resolutions of the cat paradox are really viable. Next slide, please. Okay, well, but all those interpretations were based on assuming that quantum mechanics was indeed the complete description of the physical world at all possible levels. Now let's suppose we make the opposite interpretation. Let's assume that quantum mechanics breaks down at some point en route from the atom to the cat. Now, you say, well, fine, that's a nice sort of qualitative statement. Are there actually detailed theories along these lines? And the answer is yes. There are several, of which probably the best known is the so-called GRWP theory. That's Girardi, Rimini, Weber, and Pearl. I won't go into that in detail for reasons of time, but crudely speaking, what it does is to ensure that quantum mechanics does work fine at the microscopic level, but by the time you get to the everyday macroscopic level, then events do or do not occur as we normally assume in our common sense description. As I say, so that's just one of several possible alternative approaches. I won't stick my flag on any particular one of these, but I will just consider a general class of theories which has this property, which I call macrorealism. In other words, quantum mechanics works fine at the microscopic level. By the time we get to the everyday level, things have changed so that events do or do not happen as we normally assume. Okay, next slide, please. So, well, that of course raises the question, well, is quantum mechanics in fact the whole truth about the world at all levels? How would we tell? Well, now we have a problem, you see, because if all everyday scale bodies have the property that the interference term is randomized by decoherence, then we'll always get the common sense result. That is, no matter whether we believe quantum mechanics or we believe macrorealism, the experimental result will just be the same. They'll be as if one path or the other will follow. So we will not be able to tell. So we must then be able to find some everyday scale object where decoherence is not effective. Does anisotropy exist? Well, when I and a few other people started, as it were, pushing this program way back around 1980, which seems a very long time ago now, there was a huge skepticism in the quantum measurement community. This is complete nonsense. You're never going to find a macroscopic system where decoherence is sufficiently ineffective. You have a chance of doing a meaningful experiment. They're wrong. By now, it's clear that not just one, but several different, in fact, many different such systems exist. What are the prerequisites? Well, first of all, the difference of the two states must be at what we could reasonably call the everyday or macroscopic level. Nevertheless, the relevant energies which control these states must be at the atomic level. There must be an extreme degree of isolation from the outside world, and finally, must be a very low intrinsic dissipation, because it turns out that intrinsic dissipation has much the same effect qualitatively as the effect of the outside world, the environment. Now, here when we come to actually try to do the experiment and try to do the appropriate analysis for it, we run up against a problem. Suppose that we do the experiment and it comes out in favor of the quantum mechanical predictions. Then everyone's quite happy and they say, yeah, well, we could have told you that without spending $500,000 on it. If on the other hand, the result comes out against, let's say in favor of macrorealism and therefore against the predictions of quantum mechanics, then the roof is going to fall in on us, because people are going to say, look, you guys in condensed matter physics, and we'll see that our examples mostly do come from condensed matter physics, you guys in condensed matter physics are just too naive for words. You have this messy system full of impurities and dislocations which you don't know about in detail. It's sitting on a lab bench which is vibrating with thermal vibrations. It's bathed in the black body radiation field, etc., etc. How can you possibly know enough about the system at the microscopic level to actually do a reliable quantum mechanical calculation? Well, they're right, you couldn't. But very fortunately, it's turned out there is an alternative procedure. It turns out that what we can do is to look at the experimental behavior in the classical limit, that is the limit in which classical and quantum predictions coincide. And from that, we may be able to infer not the whole microscopic description, but enough of it to be able to do a reliable quantum mechanical calculation. And that's really been how the theory has proceeded over the last 40 years or so. Most people, I think, who've been substantially involved in that would agree that this does appear to be more or less a reliable procedure. So anyway, what are the possible systems? Well, at this point I'm going to skip. I think in view of the time, I should skip the next 3 or 4 slides and just go to about the 5th one. Can you go just, okay, so skip, yeah, okay, I think we can stop on this one for a moment. Here is, this is nearly, but not quite, the kind of system we want to consider. This is a single superconducting ring subject to a certain external magnetic flux. Now it turns out, and this is the 4 slides I basically skipped, but these are, I think it's fairly well established, it turns out that in a superconductor, the carriers of electric current are the so-called Cooper pairs, that is a sort of two-electron particle or quasi-particle which has twice the electron charge. And in this kind of geometry, there is a quantization for these Cooper pairs, namely the circulation, the integral of the velocity around the ring, is given by the expression h over 2m n minus phi over phi 0, where n is an integer and phi 0 is the so-called flux quantum h over 2e. As I say, you have to take that on trust, I'm afraid. But anyway, it has the following consequences. And furthermore, very importantly, the energy is proportional to k squared, not to k. So this has the following consequences. First of all, if the flux is 0, then the ground state is unique. It must please stay on the one I was on. Please stay on the slide I was on. That's one. I think 15. 15. Slide 15, please. Thank you. Yeah. Right. So if the external flux is 0, then n has to be at 0 to minimize the energy. All the pairs are at rest. That's very boring. Not interested in that. If, on the other hand, the flux is half of the flux quantum, then you see that the ground state is doubly degenerate. That is, you have two states with exactly the same energy corresponding to n equals 0 or n equals 1. So in other words, you have two possible ground states, in one of which all the pairs are rotating clockwise, in the other they're all rotating anti-clockwise. Now, very important to be clear that a state with 50% of the pairs rotating clockwise and 50% anti-clockwise is not allowed as a ground state. It's strongly forbidden. It has a very large energy compared to those two states we've identified. Okay, next slide, please. Yeah, okay. This is closer to it is really the real system. We've simply prettied up the system on the last slide by putting into the ring a so-called Josephson junction. And if you're not familiar with the Josephson junctions, you can just imagine this as a sort of gate which will allow the Cooper pairs to pass but with increased difficulty. And then it turns out that if you go through the quantum mechanical calculations, the result of this is to say that in fact the ground state is not one of these states, that is all rotating clockwise or all rotating anti-clockwise, but rather a quantum superposition of the two. That is the formula psi equals 2 to the minus a half clockwise plus anti-clockwise. And let me emphasize again, this is not a state in which half the electrons are rotating clockwise and half anti-clockwise. It's a quantum superposition of two states in each of which all of the electrons are doing exactly the same thing, either rotating clockwise or rotating anti-clockwise, but it's a quantum superposition of those two states. Now, again, I think to speed things up a little, I'll skip the details, but there has been evidence now for about 20 years that such states exist, and in fact nowadays they are widely used in building elementary quantum computers. So they certainly exist. The system does behave in this way. However, can we go to the next slide, please? No, next again. Yeah, okay. So what next after this? Let's skip this one. Yeah, all right. Okay. So it does look as if the behavior of these systems, which are reasonably macroscopic, everyday level, it does seem their behavior is consistently described by quantum mechanics. However, I'm a Popperian in my philosophy of science. I don't believe that any finite series of experiments could prove quantum mechanics to be right at this level. However, I do believe in falsificationism. I do believe that with certain caveats, a finite number of experiments may be able to prove that a certain class of theories is wrong at this level. And in this case, the relevant class of theories is the so-called macrorealistic ones. So let us see if we can actually do a test of macrorealism versus quantum mechanics using this kind of system. So for this system, incidentally, nowadays it used to be called an RF squid way back in the 80s. Nowadays it's usually called a flux qubit because of its use in quantum computers. So for a squid or flux qubit, let's define the class of macrorealistic theories by the following postulates. First is the following. We know that whenever the system is observed, we indeed find it to be in either the clockwise or the anticlockwise state. That is, all electrons going clockwise or all going anticlockwise. That's the case whenever we observe it. And that's an experimental fact. But now let's make the assumption that it always is in one of these two states, whether or not it's observed, with allowance made for short transit times between them, which we can take into account. That's postulate number one. Postulate number two, we can in principle determine whether the state is plus or minus without any effect on the subsequent behavior. That's what I call non-invasive measurability. And finally, the third postulate I've called induction, but that's probably a bad name. What I really mean is the standard arrow of time. That the past determines the present and the present determines the future and not vice versa. Then it turns out that there's a certain quantity k whose value can be directly inferred from an appropriate series of measurements. And we'll make some firm predictions for k. First of all, any macrorealistic theory will predict that that quantity k has to be less than or equal to 2. And I think everyone pretty much agrees on that. Secondly, if we treat the system as ideal and completely isolated and no internal dissipation, etc., then the quantum mechanical description says that k is 2.8, which, needless to say, is not less than or equal to 2. Again, I think most people agree about that. Finally, quantum mechanics with all the real-life complications, that's a more tricky one. But I think most people who've actually seriously thought about this question would agree that we can reliably predict that with appropriate engineering, etc., k is less than 2, k is certainly more than 2, but it's still less than 2.8. And therefore, to the extent that the analysis of C within quantum mechanics is reliable, you can force nature to choose between macrorealism and quantum mechanics. And Anupam Gurg and I made this prediction way back in 1985, and it's taken a long time to really implement it. Can you go to the next slide, please? Yeah. Okay, so here are the possible outcomes. First of all, it could be the experiment doesn't work, but then, well, I simply trust my experimental colleagues to improve it, so it does work, essentially. Second possibility is that k is greater than 2, which would mean that macrorealism would be refuted. And third is that k is less than 2, in which case quantum mechanics, well, prima facie, quantum mechanics would be refuted at the everyday level. Of course, in real life, is never going to happen, but in an ideal world, that would refute quantum mechanics at the everyday level. So as I say, for a long time, it was really not known what was the answer. And that was the situation up to October 2016. Then the experiment was done, which is not, in fact, precisely the one that Anupam and I proposed in 1985, but is pretty close to it. So I think most people agree it's essentially equivalent to the experiment we proposed. Next slide, please. And indeed, the experiment was done in November of 2016. It was done by a consortium at NTT in Japan. I'm a co-author of that paper, but my role was minor in it. The main result is the experiment. And what that experiment found is that the result is indeed B. That is and it's B by more than 80 standard deviations. In other words, it does look, well, in fact, it seems fairly definite that macrorealism does fail at least up to the level of superconducting devices. It is not true that these superconducting devices, which have available to them two apparently alternative, macroscopically different states, it is not true that they're always in one state or the other. Sometimes they indeed appear to be in this weird quantum superposition. So, of course, that raises the question, where do we go from here? Well, of course, we could just go to bigger objects, larger flux qubits, etc., etc. I don't think that's particularly interesting. What's a lot more interesting is to go in the direction of increased complexity. For example, could we do an experiment to determine whether the human visual system, which is much closer to our own direct consciousness, that visual system itself can be in a superposition of states? Well, it is fairly definite now that a single rhodopsin molecule in the human eye can be triggered to go from one conformational state to another by something like 6 photons. Now, a quantum superposition of the vacuum and a 6 photon state is by now not that difficult to create. Several groups have done that. So the idea would be to try to shine such a superposition on the human eye and to find out whether indeed the rhodopsin molecule is in a state of quantum superposition or not. Well, a couple of colleagues of mine at the University of Illinois, Paul Priat and Wang Xiao, did actually start that experiment a few years ago, but alas, it turns out the human eye is a very inefficient detector, and so to take enough data to be meaningful would take much more time than the lifetime of the graduate student involved. So that didn't, although it produced some very nice results on classical psychophysics, it didn't perform the function we originally intended. But nevertheless, there are increasingly proposals to go in this direction, and I think it is incredibly important to continue probing quantum mechanics towards the level of the everyday world. What do I personally believe? I personally believe it's going to break down. Now, at what point it's going to break down, I can't tell you. How it's going to break down, I certainly can't tell you. That it's going to break down, I think I'm pretty sure. And so that would be my bet on the future. But this is where we are now. Thank you.
Thank you. Thank you very much, sir. That indeed was a mesmerizing lecture. And let me just take up a few questions. There are plenty of them, but I'll take up first few of them. So the first one is, what does negative probability amplitude indicates?
Well, I think that really depends on your interpretation of the quantum formalism. The fact that the amplitude for okay, I should say there's a certain amount of arbitrariness here. I did oversimplify things. The fact that I described in the thought experiment that I considered, that I described the, for example, the amplitude to go through path B as positive and the amplitude to go through path C as negative, that was really a totally arbitrary choice. I could have done it the other way around. It could have been the amplitude for B, which is negative, and the for C, which is positive. It's only the relative signs of the amplitude which are important in the formulae. So I think really there is no particular physical significance to a particular some amplitude being positive or negative. As I say, it's only the relative signs which matter.
Okay. So this is one of the questions which have been asked by several attendees. What is the exact meaning by saying that AB and AC simultaneously exist, but neither B or C they are selected? In one of your slides.
Well, I said yes. I said I thought that the prediction is that whenever in a case where you only have A sub B or A sub C, you get automatically get the common sense result. In order not to get the common sense result, you've got to have both your amplitudes non-zero. Now, it's also the experimental observation is that it's well, trivially, it's only when both paths are open that you get the interference phenomenon occurring. So, putting the experimental result together with the way that quantum mechanics describes the situation, I claim that it's a very natural conclusion that whenever the quantum mechanical description says that A sub B and A sub C are both non-zero, then in general it is not the case that each individual system selects either B or C. If you ask what is the status of that statement, I find it a bit difficult to go beyond saying that it's a very natural conclusion from the combination of the experimental results and the quantum mechanical description of them. I think I'd have to, in some sense, be a minimalist at this point and simply fall back on the statement. Well, all I'm saying is that we cannot make the positive statement. I really can't tell you. Sorry, let me start again. The only conclusion we can draw is that there is one statement which we cannot make, namely that each system chose either B or C. If you ask me what positive statement that implies, I don't think that the answer is unique. The answer could be, well, you just shouldn't be worried about this question. You shouldn't be worried about what is actually happening. That would be, for example, the answer given by advocates of the statistical interpretation. As I think David Mermin or some other famous person said, just shut up and calculate. So I mean, frankly, I don't think I can go beyond that statement.
Okay. So I'll take up the last 3 to 4 questions which are there quickly. The first one is why orthodox resolution considered every time and not the realistic resolution regarding the position? In one of your slides, you have shown orthodox resolution, and the other is the realistic resolution. Yeah.
Oh, why do people consider the orthodox resolution as opposed to the macrorealistic resolution? Well, I mean, I don't. Not everyone does. I mean, there is I would say probably if you just take a random sampling of practicing physicists, yeah, you probably would find that the majority embrace the what I call the orthodox solution, but there is a substantial minority, which sort of includes me, which would embrace some qualitatively some version of the macrorealistic solution. As I say, so you just have to place your bets. My bet is in favor of macrorealism.
Okay. I'll take up the next one. Is the concept of decoherence analogous to the collapse of wave packets on measurement for which we are getting a particular result?
Okay, I think you have to have a bit of technicality here. No, I don't think that the idea of decoherence is equivalent to the idea of collapse. But the simplest way of analyzing this is in terms of the so-called density matrix. Crudely speaking, in the kind of situation I've discussed, if you work in a basis where the two basis states are path B or path C, say, then in the kind of situation I've discussed, the original description at the microscopic level would be that the density matrix has not only diagonal but also non-zero off-diagonal elements. The diagonal elements are both, it's a 2x2 matrix, so the diagonal elements are both non-zero, but you also have non-zero off-diagonal elements. Now, in that situation, decoherence would mean the removal of the off-diagonal elements without any effect on the diagonal elements. The diagonal elements would both still be non-zero. Collapse would mean that you somehow select, or nature somehow selects, one of the diagonal elements. So these two are actually different processes in the business of getting out a definite result. So I think they are different.
Okay. Okay. I'll take up the last two questions, sir. The first question, it has two parts. Can the Mandela effect provides the existing of parallel universe?
Can which effect?
Mandela effect.
I'm sorry, what is the Mandela effect?
That's okay. I'll pass it on to the next one in that case. This is related to the. Just a second. Just scrolled up. Yeah. Okay. So this is by Malcolm Levitt, and he says that the common description of the two-slit experiment expresses the paradox in terms of one of the paths being observed. That seems to infer a role for human consciousness. Would you agree that a more useful description would talk about one of the paths being followed to interact with a macroscopic object?
Well, I'm not really sure that gains you very much. Certainly, there have been many discussions of the correct description of the interaction of an electron, or let's say, with some macroscopic detector, but and they usually result in a description in which the state of the electron or atom gets entangled with that of the detector. But that doesn't really solve the problem, because in the enlarged space, the enlarged Hilbert space, which is the direct product of that of the electron and that of the detector, you still have a superposition. So, so I don't myself feel that simply entangling the atom or electron with the detector really gets us any further in the discussion of this.
Okay, I'll take up the last question then. On one of the slides, that is slide number 18, you have explained the squid experiment. How can we have non-invasive measurements? Won't the wave function collapse?
Well, yes, indeed. Look, let's just imagine the two-slit experiment again, and let's imagine Heisenberg's gamma ray microscope experiment, in which you shine a gamma ray photon on one slit but not on the other. So and then you argue that if the electron comes through one slit, then it scatters the photon, whereas if it comes through the other, it doesn't. Now, in quantum mechanics, the fact that you don't see the photon scattered also by itself constitutes a measurement. So yes, you would get collapse. Within the quantum mechanical description, an observation that a photon is not scattered would tell you that the electron has gone through the slit C, and that would be essentially equivalent to collapse. However, you have to realize that by construction, macrorealism tends to be different from quantum mechanics. So in macrorealism, if I shine a flashlight on one slit and see nothing, I have not affected the electron, because the electron already was either going through B or through C. And in fact, if I don't see it, it must have gone through C. And by shining my flashlight on B, I could not have affected its behavior going through C. So that in that respect, quantum mechanics explicitly contradicts what quantum mechanics says has happened. So
Okay.
did I say that right? I'm getting tired. Did macrorealism actually make a statement which is opposed to the statement made by quantum mechanics?
Sure. Thank you. Thank you very much, sir. Now, may I request Professor Vinay Gupta to kindly give some concluding remarks, followed by Professor Anurag Sharma.
Thank you, sir, for delivering excellent talk. and especially enlightening about the doubts about the paradox of the quantum mechanics, sir. We are grateful to you, sir. And we request you that in future also you should try to associate with us, sir. Enlighten us in future also, sir. Thank you, sir.
Thank you. Thank you very much, Professor Vinay Gupta. I request Professor Anurag Sharma.
Yeah, I mean, this was a great lecture. Like earlier, we had the other one also. And it's really a pleasure that we could host, although not physically, but only through virtual mode, Professor Leggett, and we could expose our students to the great knowledge that he could impart. Thank you very much.
Thank you. Thank you very much, sir. Thank you very much, Professor Leggett. Thank you very much, Professor Anurag Sharma, Professor Vinay Gupta. And on behalf of the organizer, I would like to thank once again Nobel Laureate Professor Tony Leggett for sparing his valuable time and enlightening all the students, the attendees, the faculty members from all over India itself. We have seen very large gatherings, but this time I'm seeing more than 475 were there at one time, and still now I think it's more than 300 participants are still there. Thank you very much. So may I have the permission to close the session, sir?
Yes, please, please do. Thank you.
Thank you.
Thank you.
Thank you very much, sir. Thank you.